Welcome back. In this last example, we're looking at the integral of x over the square root of 3 minus 2x minus x squared dx. Now here this doesn't look like any of the examples that we gave, because inside the square root we don't have just a constant squared minus x squared or vice versa or even a plus in the middle. We have this extra x term that doesn't seem to belong there. So how can we handle integrals like this? Well, the answer is we complete the square. Let's do this off to the side. So complete the square on the left side. We're going to take what's inside the radical, the 3 minus 2x minus x squared, and complete the square. So the 3 we're going to leave out here, and then the two variable terms, what we're going to do is factor out the coefficient in front of the x squared, so that's a negative. And I'm going to go ahead and flip the terms around, so we have the x squared first, and then we have plus 2x next. It's the same thing. If you distribute the negative back, you'll get the negative x squared, and you'll get the negative 2x as well. They're just in a different order. But what we're trying to do here is rewrite this so that it's a constant squared minus, and then something that involves the variable squared. That's going to be our goal. So to do that, we have to complete the square. We have to figure out what number is going to go inside to make this trinomial factor as a perfect square. So what is that number going to be? If you said plus 1, that would be correct. So what you do is you take the coefficient in front of x, which is 2, you divide that by 2, you always divide by 2, and then square it. So 2 divided by 2 is 1, 1 squared is 1, so that's what you're going to add there to make this into a perfect square, so that you can factor it as something squared. Now that changes the expression, right? Adding 1 inside the parentheses here is going to change the overall expression. But how does it change it? Well, adding 1 inside the parentheses is really like subtracting 1 to the overall expression, and that's because of this negative that would distribute to the positive 1, making it a minus 1. So to cancel off the effect of the minus 1, we're going to have to put an extra plus 1 outside the parentheses. So we have 3 minus and then quantity x squared plus 2x plus 1, and then close the paren, and then another plus 1. Now, this may seem like doing plus 1, isn't that doing plus 2? But remember, this plus 1 inside the parentheses is really a minus 1 with regards to the expression. So we have to balance it out by putting a plus 1, or cancel it off, I should say, by putting a plus 1. That way we're not actually changing the values of this expression. Alright, so we can add the plus 1 on the outside of the parentheses to the 3 to give you 4, and then factor what's inside the parentheses as x plus 1 squared. So now we've got it written in the form a squared minus x squared. The only thing is, instead of an x, we have an x plus 1, but that's no big deal. What we can do is just let x plus 1 equal whatever trig function we want to use for our substitution. Let's see how that works over here. Make a little dividing line. So taking the next step for this integral, this is the integral of x over the square root of 4 minus quantity x plus 1 squared, and then we have a dx. So now we're going to do our substitution, our trig substitution. We're going to let x plus 1 now equal, let's see, this is an a squared minus x squared. It's a sin to ask your professor. And so if you go by that mnemonic, then we're going to use sine. We're going to write 2 sine theta, where theta is between negative pi over 2 and pi over 2. Okay, now if we take the derivative of x plus 1 is just going to be dx. I mean, dx d theta, but we move the d theta over to the right. So we have 2 cosine theta on the right side, d theta. And now we can replace all the x's with thetas. The x on the top will be, let's see, what will the x on the top be? This is a little bit tricky because we have x plus 1 equals 2 sine theta. So what does x equal to? So if you said 2 sine theta minus 1, that would be correct. You just subtract the 1 over, and that would give you what x is equal to. So 2 sine theta minus 1. So you just use that relationship between x and theta and solve it for x by subtracting the 1 over. Now in the bottom, we're going to have the square root of 4 minus, and then x plus 1 gets replaced with 2 sine theta. So we're going to have that squared, which is 4 sine squared theta. And the dx is 2 cosine theta d theta. I just want to point out that this is one of the biggest mistakes I see in these trig integrals that really gets students stuck, which is forgetting to replace the dx. I know sometimes in Math 180, like, what are those dx's and d thetas? I don't have to write them, right? Well, the more you go in calculus, like for example right here, the more it's going to become really important to write the dx. It's going to remind you that there is something there. There is something there. So when you're doing a substitution, that needs to get replaced as well. Also, when you go down the road to Math 280, Calculus 3, you're going to deal with multiple integrals. You'll have double integrals or triple integrals, and each of those integrals is going to have a dx or a dy or a dz or a d phi or a d theta associated with it. And so you have to make sure to write all those things out, otherwise you have no idea what order you're integrating in. So anyway, just to point out, in the long run, make sure you write your dx's or your d thetas or whatever is there. It'll help prevent you from making mistakes, and also you'll be a better mathematician, and I'll pat you on the back. All right. So what do we have to do next? Oh, let's take that radical and break it down by factoring the 4 out. And we have, in parentheses, 1 minus sine squared theta. So then this gives us the square root of 4 cosine squared theta, which is 2 cosine theta. So we get the integral of 2 sine theta minus 1 over 2 cosine theta times 2 cosine theta d theta. And this is great because the 2 cosine thetas cancel, and we get the integral of 2 sine theta minus 1 d theta. All right, integrate that, and we have negative 2 cosine theta. And then the integral of 1 with respect to theta is theta, and we have a little plus c at the end there. Now coming back from theta into x, we're going to use that relationship that we had set up. So here we're going to write sine theta is x plus 1 over 2. Take that relationship, divide the 2 over, and we get sine theta is x plus 1 over 2. Make our little triangle. So sine is going to be opposite, so the x plus 1 is opposite, the 2 is hypotenuse, and the other side is, well, by the Pythagorean theorem, the square root of 2 squared minus x plus 1 quantity squared, which would give you 4 minus x plus 1 quantity squared. But remember, that expression was equal to 3 minus 2x minus x squared. That was, after we had completed the square, and then before we completed the square. So we're actually going to write it using the before completing the square version, because that's more in line with what we started with. It's just a nicety. It doesn't really matter which way you write it. Being courteous to the people who made the problem. All right, so cosine theta then in this triangle would be adjacent over hypotenuse. That would be this radical over 2. So we have the radical 3 minus 2x minus x squared over 2. And then minus theta, which is going to be inverse sine of x plus 1 over 2. We'll put our little plus c at the end. Inverse sine because we can take that relationship, sine theta equals x plus 1 over 2, and just do inverse sine to get theta. So the last thing maybe would be to cancel off these 2's. We still have a negative in front. So we have negative the square root of 3 minus 2x minus x squared minus inverse sine x plus 1 over 2 plus c. So that would be the answer for that integral. And whoops, it just said here's how you would start the following integral. Well, we did it all the way. Guess that's what happens when you have too much fun with trig integrals. You just do them all the way. Not trig integrals, trig substitution. Trig integrals was 7.2. Okay, so thank you so much for watching, and hope you learned a new tool for your integral tool belt. See you next time.